the title of the paper I'm going to present today is Auctions with Withdrawal Rights, a Foundation for Uniform Price. And this is joint work with Ali Haberman, who's an outstanding graduate student at Stanford. This is a paper about auctions with correlated value. So to put things in context, let me just remind you what we know about this setting. So in the presence of correlation, optimal selling mechanisms tend to be very complicated because they tend to screen bidders in addition to based on their values, based on their beliefs. And this is because when information is correlated, each different types of bidders will have different beliefs about what other bidders' information. And one way of implementing this is to require bidders to take a side bet about what others are going to report in order to participate in a mechanism. That's how things work in theory. But in practice, things look quite different. I think it's reasonable to think that bidders' information is likely to be correlated, and yet we don't see these side bets being used in practice. Instead, more common auction formats are things like second price or uniform price or English auction. So, in our view, this poses a concern for the standard Bayesian mechanism design approach to thinking about auction design with correlated information, given that there's such a big gap between the optimal mechanisms in theory and mechanisms that we think are used, that we see used in practice, and that we think might be usable in practice. So the goal of this paper is to provide a foundation for the uniform price auction that applies in settings with correlated information. And it's going to be based on a restriction on the seller's ability to enforce commitments by the bidder. So to be a little bit more precise, what our main result is going to show is that if bidders can withdraw from an auction ex post, so that is after learning the outcome of the auction, then a uniform price auction is going to be optimal even in settings with correlated information. And this result is going to hold exactly in a large market limit in which the number of bidders in the auction and the number of units of the good for sale both go to infinity at the same rate. And we're also going to have some simulations that show that the uniform price auction is approximately optimal with small numbers of agents. So this result is going to hold both with private values and with interdependent values. And because it holds with private values, it's not driven by forces like the winner's curse that are going to apply in settings with interdependent values. It turns out, one natural implication of the ability to withdraw ex post is that the seller cannot implement anything that's not ex post individually rational. But that also turns out not to be what drives the result. And actually, what's important is an interaction between the withdrawal right and the incentive constraint. So some other people have put more nicely what this interaction is than I could. I'm going to quote a paper of Quant and Jehiel, which is that when considering a deviation, an agent is going to take into account the fact that he can opt out if things turn out badly. So when I can withdraw ex post, there are going to be additional incentive constraints where I may be willing to misreport and then withdraw depending on what happens in the auction afterwards. And it's these additional incentive constraints that drive the optimality of the uniform price auction. So before getting into the meat of the paper, I want to spend a little bit of time motivating withdrawal rights, which is, I think, the key novel feature of our model. So in the EU, there is an explicit withdrawal right, which applies for 14 days for all distance sales, and this also applies for online and remote auctions. I guess I had a quote from the EU Consumer Rights Directive, because for American audiences, I need to say a little bit more about the withdrawal right, but maybe I'll skip that part for this audience. I think another way of thinking about what the withdrawal right could represent is something more implicit, which is that when thinking about a complex asset or a business being sold by auction, after the finalization of an acceptance of an offer or letter of intent, buyers often conduct what's called confirmatory due diligence to verify that the representations of the seller regarding the condition of the asset or business are correct. And in practice, there will be some small issues which provide an implicit channel for bidders, especially the winner of the auction, to be able to withdraw exposed. So let me pause here to see if there's any questions about kind of the setup. If not, let me move on a little bit. So in terms of related literature, I mean, there's a large literature on mechanism design problems with correlated information. And I think one focus in this literature has been to determine when the seller can extract the full surplus from the bidders in the auction. And our contribution here is to go beyond that issue and to think about when a simple mechanism is optimal, even in the presence of correlated information. There have also been some papers that have provided foundations for the uniform price auction that are based on robustness. And we're going to instead do a completely Bayesian analysis of the seller's problem, but we're going to need to work with a large market in order to get exact optimality results for the uniform price auction. And there have also been some other work on withdrawal rights in dynamic settings. And we're going to show, and in there, withdrawal rights also simplify the optimal selling mechanism in a strong way. And here we're going to show that a similar type of simplification arises when applying withdrawal rights in a static setting with correlated information. So I think I can then jump directly into the model. So the way we're going to think about this is there's going to be a one-dimensional state, which I'll call S. And this is common across all bidders, and there's a common prior. So this could represent the overall level of demand for the asset. And there's going to be a continuum of bidders, each of whom is going to have unit demand. They're going to receive a private signal that's drawn from a state-dependent distribution. And we're going to assume that this family of distribution satisfies the strict monotone likelihood ratio property. So in higher states, higher signals are more likely in the likelihood ratio set. So the source of correlation here is that if I'm as a bidder receive a higher signal, I'm going to believe that the state is more likely to be higher, and therefore that other people's signals are also more likely to be higher. So the correlation is all through this one-dimensional state. A crucial assumption is that bidders don't know what the state is before participating in the mechanism. So they only know their private signal. The seller is going to be able to infer the state from the reports, because if you observe reports of a continuum of bidders under an incentive-compatible mechanism, that's going to be sufficient for you to pin down the state. It would be equivalent. Nothing in our analysis would change if the seller knew the state in advance. And in each state, type theta is going to have a value for the good that depends on potentially on their signal and on the state. And we're going to assume that this value is strictly increasing in your signal and weakly increasing in the state. So there's two natural cases that one can think about. One is the case of private values, where the value that a type theta attributes to the good in state S is just given by their signal. And that's the case I'm going to focus on for most of the talk. Second case is where values are interdependent, so where the value also depends on the state. And I think when thinking about motivation for withdrawal rights in practice, it's the interdependent values case that probably comes to mind. Right? I mean, one reason why people might think about wanting to withdraw is when there's a winner's curse, or they take a look at the good and realize it's not as good as what they thought. And we're going to be able to capture that. I'll talk about that a little bit towards that. And so in terms of the auction part of the environment, there's this continuum of bidders, and the seller is going to have k units of a homogeneous indivisible good available for sale, where k is less than 1. So you can sell to some fraction of the bidder. And for this talk, I'm going to assume that the seller is constrained to sell all the units of the good and to sell them efficiently. It's also not important to our results. It just makes things simpler in terms of stating the results and explaining why they're true. We relax it in the paper. Let me pause here again to see if there's any more questions about the setup. Okay. If not, I think before getting into our analysis, I want to explain a little bit. Yeah, so the outline is I'll start talking about the private value case. I'll then talk about an extension with interdependent values, and then I'll explain how the proof works. So for the private value case, before getting into our results, I need to tell you a little bit about what withdrawal rights are. So because the setting is non-standard, I just want to remind you of what incentive compatibility means in this setting. So we say a direct mechanism is incentive compatible, a Bayesian incentive compatible, if for all types theta and all reports theta prime that the type theta might make, the expected utility from reporting theta is at least the expected utility from reporting theta prime. Now, there are two things to keep in mind here. One is that the expectation, the main source of uncertainty here is the state. We could allow for stochastic mechanisms. My notation is not really going to allow for that, though. And second is that different types have different beliefs about what the state is because of the correlation. And both of these expectations should be taken with respect to the beliefs of type theta. And we're thinking about a deviation by type theta. Now, withdrawal rights is going to be a similar condition, except that when you deviate, there's something else you can do, which is if things don't work out, you can withdraw. So mathematically, rather than thinking about the expected utility from reporting type theta, the value from deviating is the expectation of the max of the utility from reporting theta prime and 0. So the interpretation here is that after reporting theta prime and after the auction is run, the bidders can then freely withdraw exposed. And if they do that, then you get utility 0. And under private values, in order to figure out whether I want to withdraw exposed, all I need to do is I need to learn what my allocation and payment are. And so if I have to pay more than what the good is worth to me, or if I have to make a payment when uh, when I'm not getting the good, then I'm just going to walk away. So one thing is withdrawal proofness is going to imply Bayesian incentive compatibility, right? Because the possibility of withdrawal only makes deviations more desirable. It also implies that the mechanism has to be exposed individually rational with probability 1. Because one thing I could do is I could just report truthfully, and then if I don't like what's happening under truthful reporting, I can withdraw exposed. And if I'm getting a negative utility with positive probability, I'm going to want to withdraw exposed and be able to profit from it. Now, the converse of this implication is not true. So there are mechanisms that are Bayesian incentive compatible and exposed individually rational, but that are nevertheless not withdrawal proof. And the reason is that we need to be concerned about double deviation, where I misreport and then I withdraw exposed if things don't work out. And Bayesian incentive compatibility, neither Bayesian incentive compatibility nor exposed individual rationality imply that these double deviations are not desirable. And that's because when I misreport and I withdraw, there may be situations in which I, as the deviating type, want to withdraw exposed, where the type I'm mimicking wouldn't have wanted to withdraw exposed. And it's those double deviations that are going to play a key role in our analysis. Now, despite this gap between withdrawal proofness and ex post individual rationality, the standard ex post individually rational auction formats do turn out to be withdrawal proof. So, for example, the uniform price auction and the standard equilibrium of PS bid auction. I'm going to give you an example in a little bit of a mechanism that's Bayesian incentive compatible and ex post individually rational, but not withdrawal proof. It's not going to be a normal mechanism that you've seen before. So I think the fixed ideas and both to explain withdrawal proofness and kind of the key forces at play in our result, I want to give you an example. So in the example, there's going to be half a unit of the good for sale. So you can sell the good to half of the bidder. And rather than a continuum of states, I'm going to do it with three states, which are 0, 1, and 2. And in each state, values are going to be distributed on the interval 0 to 200. I'm not going to tell you what the value distributions are. They're a little bit messy to make the mechanisms look very simple. But the market clearing price, this example is going to be set up so that the market clearing prices in the three states are 10, 40, and 80. The median value of the bidder in state 0 is 10, in state 1 is 40, and in state 2 is 80. And the question we're going to be thinking about is what's the optimal ex post efficient mechanism among various classes of incentive compatibility and individual rationality constraints. So I'm going to show you mechanisms as menus, which are going to take the following form. So when you're restricting to efficient mechanisms in terms of when each type might be allocated a good, there are only four possibilities. The lowest types are never going to get the good. Types that are a little bit higher are going to get the good only in the low state. Types that are a little bit higher than that are going to get the good only in the lowest two states, 0 and 1, and the highest types are always going to get the good. And for each of these possible allocations, the mechanism needs to specify not just one payment, but three payments. A payment in state 0, a payment in state 1, and a payment in state 2. And because bidders have different beliefs about the state, you can't collapse these three payments into a single payment. So let me just show you what the uniform price auction looks like. So what's that going to be? Well, people who never get the good never pay. They get the good only in state 0. I just need to pay the market clearing price of 10 in the low state. If I get the good only in state 0 and 1, I need to get the market clearing. I'm going to have to pay the market clearing price in each of those two states, but pay nothing in the third state. And if I always get the good, I'm going to pay the market clearing price in all three states. Okay, and this mechanism has an expected revenue of 21 and so let me show you what the optimal mechanism in the standard model. So that's under the optimal efficient mechanism subject to Bayesian incentive compatibility and interim individual rationality. It's going to be something quite complicated. By the way, there's many optimal mechanisms. I'm just going to show you one of them. So you can arrange it so that people who never get the good never pay. If I get the good in state 0, I'm going to be paid 746 in state 0. I'm going to pay 288 in state 1. And if I get the good in both of the low two states, I still get that payment in state 0, but I need to pay a bit more in state 1, 328 in state 1. And if I always get the good, I also need to pay something in state 2. And this mechanism has a much higher revenue. It has a revenue of 47.8. So here the revenue equivalence is failing because of the correlation among bidders' private information. And the mechanism here is complicated basically because there's a side bet. So one way to interpret this is that in order to get in order to be able to get the good, bidders need to take a bet that the state is going to be 0. And that's what allows you to extract more revenue from the higher type. So this was what the standard model would have told you. Let's think about but one undesirable property of this mechanism is that people are sometimes paying more than their value. So in fact, types that get the good only in state zero sometimes make payments to the seller in state one. And types that get the good in state zero and one, or always get the good, have to pay more than their value in state one. So that's these payments 288, 328, and 328 violate the ex post individual rationality condition. So let me now show you what the optimal mechanism would be under Bayesian incentive compatibility and ex post individual rationality. So here it's going to look similar to the uniform price auction, but with two exceptions. So I should say these payments, the overall payment rule is not unique, but the part I'm going to be focusing on is uniquely pinned down. So what's going to happen is that the seller, if you want to always get the good, rather than paying the market clearing price in all three states, I'm going to get paid by the seller 95 in state zero. And correspondingly, I have to pay the seller more. I have to pay the seller 80 in state one. Now, remember, the types that are always getting the good all have a value of at least 80. So there's no violation of ex post individual rationality. And this mechanism has expected revenue 24. So it's more than that of the uniform price auction. And I think intuitively what's going on here is, again, there's a little side bet. It's not as dramatic because of the ex post individual rationality condition. But this is a side bet that is compatible with ex post individual rationality. So here, basically, the high types, the way that you can make them take a bet. I mean, bets on their own are never going to be ex post individually rational, but for the combination of the auction and the side bet to be ex post individually rational, people can bet up to the surplus that they're getting from the auction. So here in state one, the high types were getting a surplus of 40 or more. And what the mechanism forces them to do is to bet that surplus in state one in exchange for getting a payment of 95, in state zero. So this mechanism is also a somewhat odd mechanism, in part due to the payment to the bidder of 95 in the low state. But I want to explain to you why this mechanism is not withdrawal proof. So if you think about microfounding the ex post individual rationality constraint as an ability to withdraw ex post, then the mechanism is no longer going to be incentive compatible. So why is that? Well, once you think about withdrawal strategies, the effective menu that the bidder space is actually bigger. So one thing I could do is I can just say, okay, my type is high. I want to buy the good in all states. Now, if the state turns out to be 1 or 2, I'm going to say, oh, sorry, I actually don't want the good, and withdraw. So effectively, what I can do by using that withdrawal strategy is to get the good in state 0 alone and get paid $95 for the privilege of getting the good. So that's something that the bidders would really like to do. And so this mechanism is vulnerable to a double deviation, where types that are getting the good only in state 0 are going to want to pretend to be high types and withdraw in states 1 and 2 to take advantage of the discount that's being offered to the high types in the low state. So that's why this mechanism, the optimal Bayesian incentive compatible ex post individually rational mechanism, is not withdrawal proof. So what's the optimal withdrawal proof mechanism is just going to be the uniform price auction. And the optimality of the uniform price auction, I just want to emphasize, is not something that's pinned down by revenue goals. So actually, even within the class of withdrawal proof mechanisms, there are other mechanisms that yield lower revenue. So for example, if you think about equilibrium in a pay-as-bid auction, that will have strictly lower revenue, basically because this is a setting with affiliation. And it turns out that the revenue ranking between the uniform price auction and the pay as bid auction persists even in this large market limit. So in order to get to pin down a foundation for the uniform price auction, it's not something that mechanically follows from withdrawal rights, but it's the combination of withdrawal rights and revenue maximization that provides the foundation for uniform price auction. So before getting into the meat of our results, I want to give you a little bit of intuition using this example for why the uniform price auction is optimal. So the key is that this is a setting with affiliation, so the linkage principle applies. So how would I want, if I start from the uniform price auction and I wanted to raise more revenue, what I would want to do is I want to link the payments of winners to the types of other bidders. Now here, the source of all correlation between a bidder's types is through the state. So effectively what I want to do is I want to link winners' payments to the state. So how could I do this? I could say, let's focus on making the bidder, the high types. If I wanted to make them pay more in the middle state, I can't really make them pay more in the high states because in state 2, the high type 80 can't really pay more than 80 without violating ex post individual rationality. So the best I could do in order to link the high types payments to the state is to make the high types pay a little bit more in state 1. So let's say instead of charging them 40, I charge them 40 plus delta in state 1. Now, if I just did that on its own, I'm going to violate incentive compatibility. Right? You can't just charge someone a little bit more like that. So if I want to preserve incentive compatibility or even local incentive compatibility, I need to offer the high types some discount in the low state. Right? There's going to be a trade-off to preserve their first order condition. Let's say I offer them a discount of gamma. Then what I'm going to end up doing is if I want to link high types payments to the state, I need to offer the high types a discount in the lower state. But now we have a problem, which is the low types are going to want to pretend to be high types in order to take advantage of that discount. So this is going to incentivize double deviations, where lower types are going to want to pretend to be high type in order to take advantage of the discount that the high types are offered in the lower state. Now, for the actual proof, things are a little bit more subtle, and that's because when you have more than 3 states, the lower types and the higher types may have different beliefs about the states in which discounts are being offered. And so you can imagine that there are changes to the payment rule that the high types like. So they see as a discount, but the low types don't like, because you can have changes to the payment rule that offer discounts in states that the high types think are more likely, but charge premia in states that the low types think are more likely. And that's what seriously complicates the whole analysis. So let me pause here to see if there's any questions, because I think at this point, I've explained to you what the key forces are. I'm just going to state things more formally and go through the proofs in the remainder of the talk. Okay. I think that's it for this example. So I think let me state for you the main theorems. The main theorem is that under private values and under an assumption on the correlation structure that I'm going to call regular affiliation, which I'll introduce in a moment, the expected revenue of the uniform price auction is greater than or equal to the expected revenue of any ex post efficient withdrawal proof mechanism. So this result provides a foundation for the uniform price auction that applies in settings with correlation that's based on withdrawal rights. And in the paper, we also provide a corresponding uniqueness there. So one side benefit here is when we impose withdrawal proofness, we formulated it in a Bayesian way, right? There's an ex post individual rationality constraint, and you can withdraw ex post, but bidders need to select their report at the interim stage. And one thing that happens here that emerges is that the optimal mechanism is dominant strategy incentive compatible, because we're in a unit demand private value setting. So the uniform price auction is dominant strategy incentive compatible. So we got dominant strategy incentive compatibility for free. So I need to explain to you what this regular affiliation condition means, though. So I'm going to just state it for you formally, and then I'll explain a little bit about how to interpret it. So it's not necessarily the most natural condition that one might have written down on correlation. But this is a condition on the mixed partial derivative of the log of the density, right? So that measures how changes in the state affect the distribution of types, or equivalently, how changes in the type affect people's beliefs about the state. So if you think about this mixed partial of log as your key quantity, what this is saying is that if I fix any type in any state, fix theta and fix s, if I integrate that quantity over all types, fixing the state, and I multiply that by the integral over all quantities of integral over all states, fixing the type of the same quantity, that has to be at most what this quantity was at theta and s. I wish I had, let me see if I have a pen here. I've forgotten how to draw things on Zoom. Oh well. So the interpretation I want to argue for is that what this condition implies is that affiliation can't be too high or too erratic. And the way I'm going to get at this is I'm going to give you a necessary condition, so something that regular affiliation implies, as well as a necessary condition for regular affiliation. So one thing that regular affiliation implies is that if I take any pair of types and any pair of states, the likelihood ratio, the ratio of the likelihoods of states S prime and S for type theta must be at most E times the same ratio for type theta prime. So if you think about each type doing a likelihood ratio test to try to figure out what the state is, what regular affiliation implies is that the likelihood ratio statistics have to vary by a factor of at most E. So this is a sense in which regular affiliation implies there can't be too much affiliation in the models. There can't be too much correlation between types. This is the sense in which regular affiliation implies that the affiliation is not too high. But one might ask, what else does regular affiliation imply? And I don't have a full answer to that, but it turns out that if the distribution of types comprises a full exponential family, like in the econometric sense, so that's satisfied by most of the examples of distributions we would write down, so like normal distribution with or without truncation, etc., then the converse implication also holds. So regular affiliation becomes equivalent to this bound on how likelihood ratio statistics can vary across states. Yes, there's a question?
Yes, hello. You have different limits in the two integrals. Is that a typo or
No, that's
something
not a
meaningful?
typo. So, I
Okay, I
see. So
missed it then.
the first one is so the first one in the first integral, the type is varying. So the type goes between the lower bound on the type and the upper bound on type. In the second integral, the state is varying. So I just normalize the state to go between 0 and 1.
Okay, so thank you.
Yeah. Let me just give you one example here. Okay, here we go. So I'm opening a little whiteboard. Okay. Can you guys see this? Okay. So the way you can think about this, just imagine I start here at some theta and s. So I'm going to draw for you theta and s. And what this condition is saying is if I integrate that mixed partial of log over all theta fixing S, and I integrate it over all S fixing theta. I multiply these two integrals, there has to be at most the mixed partial of log at the middle, at the cross point of those crosses. Let me go back to the let me go back to the slide. Yeah, so in the case of a full exponential family, this is equivalent to just bound on how likelihood ratio statistics can vary across types. So there's some extra condition that regular affiliation implies that regular affiliation entails that's implied by the hypothesis that distributions are drawn from an exponential family. And that's what we interpret as affiliation not being too erratic. So I guess an alternative way of writing this paper would have been to assume that values are drawn from an exponential family. And then this bound on ratios of likelihood ratios would have been a sufficient condition for for the optimality of the uniform price auction. We didn't go that way because we didn't want to impose throughout that values are drawn from an exponential family. But the price of that is that we need to work with a little bit more technical assumption. So without this regularity condition on the affiliation, we have an example showing that the uniform price auction is no longer optimal. I'm happy to talk a little bit more about that if there's time. But we have some simulations as well showing that even when there's a high degree of correlation, the uniform price auction still does very well, even though it's not exactly optimal. So this is all I have to say about the private value model. I just want to spend a few minutes explaining what happens with interdependent values because I think it's important for the motivation for withdrawal rights to allow for the possibility that the bidders don't know their value. So one important thing is that then in the setting with interdependent values, we need to worry about what information bidders know about the state when they're deciding whether to withdraw. And we're going to take a particular stance on that, which is we're going to suppose that all bidder signals are revealed after the auction. So this is important that it's revealed to the winners, not to the loser. So one way of interpreting this is, let's say I'm buying a house, many people bid on the house, I win. At the end, I'm going to conduct due diligence. So I'm going to hire an inspector to go and check that the house is okay. And the assumption that I'm making is that anything that anyone else saw when they were deciding whether to place a bid, and if so, how much to bid on the house, the inspector is going to figure out during the due diligence process. And in a large market, once bidders are able to figure out, so the winner is really able to figure out everyone's signals during the due diligence process, that's going to tell the winner what the state is. And so they'll be able to figure out their value. And so then the winner can make withdrawal decisions that depend on their value. So once we've set things up that way, mathematically the same definition of withdrawal proofness is going to carry over to the interdependent value setting. So a direct mechanism is withdrawal proof. If for every type in every report, the expected utility under reporting truthfully is at least the expectation of the max of the utility under misreporting and zero. And again, here the interpretation is that if the bidders can withdraw freely exposed and they get a utility of zero from doing so, this is the natural incentive constraint that one would get. And here again, withdrawal proofness is going to imply Bayesian incentive compatibility and almost sure exposed individual rationality, but we are still going to need to think about double deviation. And there is still a big enough class of withdrawal proof mechanisms to make the optimization problem non-trivial. So for example, any ex post incentive compatible mechanism is going to be withdrawal proof, but there are also other mechanisms that are withdrawal proof. So in the setting with interdependent values, our result is going to go through, but the equilibrium of the uniform price auction is going to be a little bit more complicated. Like here, once one is outside the private value context, uniform price auctions are no longer dominant strategy incentive compatible. And that's because when I'm bidding in the auction, I need to think about what winning is going to convey about the state. So the way equilibrium works is that as a type theta, when I'm bidding in the auction, if there's k units of the good for sale, I need to think about the state in which I am just on the margin between getting the good and not. So that's the state in which I am the 1 minus kth quantile type. So I'm going to call that state S star of theta. And low types are never going to reach that quantile. They're always going to be below the 1 minus kth quantile in all states. So I'll call S star the lowest state for them. And the high types are always going to be above the 1 minus kth quantile. And so I'm going to call S star theta the high state for them. And it turns out that if type theta bids their value in state S star of theta, that's going to give an ex post Nash equilibrium, the uniform price auction. So in the case of private values, this is just the usual dominant strategy equilibrium of the uniform price auction with unit demand. And what our theorem states in the interdependent values case is that under this regular affiliation condition, the expected revenue of the uniform price auction is at least the expected revenue of any ex post efficient withdrawal proof mechanism. So here, the side benefit of this is that, again, withdrawal proofness is a Bayesian condition, but the optimal mechanism is going to be ex post incentive compatible. So we get ex post incentive compatibility for free. Okay, so in the remaining about 15 minutes, let me talk about something. Let me tell you something about how the proof works. So to save on notation, I'm going to assume that the lowest type always gets an interim utility of 0. It's just going to save one term in a bunch of formulae. So the way that we do this proof is it's going to be by combining a first order approach with the use of non-local incentive constraints for these double deviations involving withdrawal. So the way I want to go about explaining the proof to you is I want to explain to you how the first order approach would work in this setting, where the key complication is the correlated information. And then I'll explain to you why it doesn't work and how we fix it. So the first bit is to explain how the first order approach works. I need to explain to you what the local incentive constraint is going to look like. So this is going to be a formula for the interim utility. And it's a little bit complicated formula, but I want to build it up for you in steps. So the formula that we get in the standard independent private values model is that for any Bayesian incentive compatible mechanism, the utility of a type theta is equal to the integral from the lowest type up to theta of the expected allocation of type theta prime. So theta prime here ranges from lowest type up to theta. So there normally, right, there would also be a term for the interim utility of the lowest type, but I'm dropping that everywhere because I'm assuming that the interim utility of the lowest type is 0. So that's how it would work with private values and with independence and with private values. Things are going to be more complicated once we have correlation. So there's going to be first thing is that expectation. We need to specify whose beliefs are going to be used to calculate the expected allocation of type theta prime. And well, there's kind of only one thing you could do, which is you need to think about the beliefs of type theta prime. Now, the key issue that correlation causes is that the beliefs of that type theta prime are going to vary with the type. And that's something that we need to take into account. The standard Meyerson term only accounts for the fact that as you change type, people's allocations and values change. But there's another thing that happens, which is that their beliefs change. And that's what this second term accounts for. This second term is an integral from the lowest type up to type theta of the expectation of the exposed utility of type theta prime times the derivative of the log of the belief of type theta prime in the type. So that derivative captures how much beliefs vary with type. So as I change the type, I'm going to change, in addition to changing the value, which the first term accounts for, I'm going to change the beliefs, which is what the second term accounts for. Now, I want to just point out that here exposed utilities are going to be cropping up. And that technically causes a lot of trouble because we know once we have exposed utilities in here, that's something that we'll have to carry around in the rest of the optimization. So this is how the whole formula works in the private values case. Under interdependent value, that actually doesn't cause too much more of an issue once we've set things up this way, which is that because there's an extension of the Meyerson formula, revenue formula by Bulow and Klemperer in the appendix of their paper, which applies even with interdependent values. So the only thing that interdependent values change is you need to take into account how the derivative of the value function in the valuation of in type. And that derivative is 1 in the private values case, and so we can drop this last time. So the key novel bit for us is this correlation correction. It has a little bit of the same flavor as envelope formulae for dynamic mechanism design models. So why is it that the first order approach fails here? Well, let's think about a relaxed problem where we just only imposed this envelope formula and no further incentive compatibility condition. So I should just say this formula for interim utilities relies on some hypothesis on the mechanism here. So a sufficient condition for this to hold, in addition to Bayesian incentive compatibility, we impose exposed individual rationality and that the mechanism has non-negative expected revenue. The reason that one needs some condition like this is basically that at some stage in proving this formula, you need to exchange an expectation and a derivative. And that requires some hypotheses that things are not too erratic. In the setting with withdrawal rights, we had exposed IR for free, so there's no problem. That condition can be relaxed a little bit, though. So this lemma only relies on Bayesian incentive compatibility and exposed individual rationality. It doesn't use any further conditions on the mechanism. And we know that the optimal mechanism subject to Bayesian incentive compatibility and exposed individual rationality is not withdrawal proof, right? We know from this example that I gave you that the optimal Bayesian IC exposed IR mechanism can give you more revenue than a uniform price auction. So if we considered a relaxed problem where we dropped all the incentive constraints except for this envelope formula, we'd have to get revenue, at least that of the optimal Bayesian incentive compatible exposed individually rational mechanism. So we do too well. We do better than the uniform price auction. So the way that we fix this is for the first term, we're going to get something like virtual values out of it that but that take into account the correlation which the standard virtual values don't allow for. And that will let us deal with all the stuff that comes from the first term. And then what's left over is these annoying terms that involve exposed utility. And the way that we handle those is by using non-local incentive constraints. Right? Basically, because when you think about double deviations involving withdrawal, the utility that the deviating type gets is going to depend on the exposed utilities of the type they're mimicking. So we use non-local incentive constraints to clean up what comes out of the second term. So let me explain to you a little bit more about how this works. So in the standard model with independent signals, so I'm going to start by explaining the private values case and then allow for the interdependent values case. So with independent private values, the relevant virtual value, right, is the difference between the value and the inverse hazard rate of the type distribution for type theta. So this is like the 1 minus the CDF divided by the PDF. In settings with correlated signals, there's a version of this virtual value that applies where you can use if you have ex post incentive constraint. So for a dominant strategy or ex post incentive compatible mechanism, the expected revenue of the mechanism is the expectation of the of an ex post virtual surplus, where you define ex post virtual value of type theta and state S to be the value minus the inverse hazard rate of the conditional type distribution in state S at type theta. Now, these virtual values allow for correlation, but they're not going to be the right virtual value in our model. And the reason is that that if in the construction of these virtual values, you need to actually use the exposed or dominant strategy incentive constraint state by state. And we only know that we have incentive compatibility at the interim stage. So it's a Bayesian constraint. So those dominant strategy incentive constraints only hold an expectation, not state by state. And basically then, if you think about this second term, this inverse hazard rate term, we can't take something that depends on the state. And so then there's kind of only one natural guess for what you could use, which is that there's one particular state that matters a lot to type theta. And that's the state in which they're marginal between getting the good and not getting the good. Like that's when you're thinking about the uniform price auction with interdependent values. This is the one that they use to evaluate the winner's curves. And that's the state S star of theta. So what we get from our analysis is what we call pseudo-virtual values, where the pseudo-virtual value of a type theta in state S is the value minus the inverse hazard rate conditional on being in state S star of theta. Now, the reason I call these pseudo-virtual values is it's no longer going to be true that the revenue of a mechanism is the expectation of pseudo-virtual surplus. There's going to be some additional terms that come up because we're choosing a state to evaluate inverse hazard rates that depends on the type. Okay, so let me skip for a moment what happens with the interdependent values case. With interdependent values, you can make all of this work. You just need to think about the V function as well. So V is going to come up somewhere and the derivative of V comes up somewhere. But that's like not the most interesting part of what's going on here. Yeah, so if signals are correlated, let me skip that too. So basically what ends up happening is that you end up with a revenue formula. And the revenue formula is going to be something, is going to have some familiar aspect and some unfamiliar aspect. I think the familiar aspect is that expected revenue is going to be given by an expectation of the pseudo-virtual surplus. And that's like the standard Meyerson formula for the independent private values model. But here, because of correlation, there's going to be some extra terms. The first extra term measures the fact that it relates the fact that if I'm thinking about a state S that's not this critical state S star of theta, then I'm using kind of the wrong inverse hazard rate. What I want to be using is the inverse hazard rate in that state, but I'm not. And so there's a correlation correction relative to this state that depends on how likelihoods vary between state S and the critical state. So that's what this derivative of a log likelihood ratio captures. There's also a correlation correction. There's also a correction for the fact that the state S star depends on the type. So you need to adjust for the fact that the inverse hazard rate of a type of type theta in state S depends on both the type and the state. And the fact that it depends on the type is something that's okay. The fact that it depends on the state is something that we need to correct for. So anyways, at the end of this, if I'm trying to think about the revenue maximization problem of the seller, let's say I've restricted efficient mechanisms, so the pseudo-virtual surplus term, there's nothing I can change about it because I fixed the allocation rule. What one can do is show that is to use the non-local incentive constraints to bound above the sum of the last two terms. So basically, this last term involves use. And I think about type theta deviating to another type and via double deviation. And that's going to tell the non-local incentive constraints will relate this u of theta to something about that u of theta s in the second term. And that's how you get a bound. So I'm not going to go through the details of how to do this, but I just want to explain a little bit about how it works. So the double deviations that we're going to focus on is where a type theta is going to report a type theta prime greater than theta, and then withdraw if the state is too high. This is exactly like the double deviations we were thinking of in the example. So to give you an example of this, a type that's getting the good in state 0 might pretend that their type is high, and then withdraw if the state is 1 or 2. And the key about these incentive constraints is that there's complementary slack. So these incentive constraints bind for the uniform price auction, right? If I report higher than my true value, that doesn't affect the payments in the states in which I was going to get the good otherwise, even without the mystery. I mean, an example of that is like in a second price auction, if I can withdraw exposed, I'm indifferent between reporting truthfully and reporting any higher value. Because the worst thing that happens if I report a higher value is that I might sometimes get the good at a price that's too high, and then I can withdraw exposed. So it's those upward incentive constraints that play a key feature in our analysis. And what we can do is construct Lagrange multipliers on these upward incentive constraints to get a saddle point of the Lagrangian using the revenue formula I just gave you. The multipliers themselves are quite complicated. It's a solution of a linear Volterra equation, but the optimal mechanism is simple, right? And the key technical point where we use the regular affiliation condition is, these upward incentive constraints are not equality constraints, they're inequality constraints. And the regular affiliation condition ensures that the multipliers are non-negative, which is what you need for multipliers on inequality constraints. So I think I'm almost out of time. Let me just say a little bit about some of the other things we do in the paper. One is that we show that the whole thing works even if the seller can implement inefficient allocations. You then need to use a uniform price auction with a reserve. And with a small withdrawal cost, we might think that you lose a deposit if you withdraw something. Uniform price auctions are still going to be approximately optimal. And this whole analysis was in a large market. But if you think about an auction for 1 unit of a good where there's finitely many bidders, we have simulations that show that a second price to English auction is approximately optimal. So to conclude, what we did in this paper is we showed that withdrawal rights provide a foundation for uniform price auctions, where in settings with correlated information, where in the standard Bayesian mechanism design approach, the assumption that private information is independent across agents is crucial to obtaining a usable optimal mechanism. And the idea is that these withdrawal rights are going to sharply limit the ability of the seller to raise revenue using side bet. So I think that's all I have to say. Thank you all for coming, and